Assalamu alaikum dear students. Welcome back to multivariable calculus series. Today we introduce two new coordinate systems that make many three-dimensional problems much easier. And these systems are cylindrical coordinates and spherical coordinates. These systems are specifically useful when a problem has circular symmetry, spherical symmetry, or cone-shaped geometry. So by the end of this lesson, you'll be able to convert between rectangular, cylindrical, and spherical coordinates, recognize surfaces described naturally in each coordinate system, understand the geometric meaning of r, theta, z, rho, and phi, and use these coordinates to describe points and surfaces in 3 dimensions. Okay, let's begin. So let's have a point xyz in rectangular coordinate system in space. So this works well for many problems, but not all. If a surface is built around a circle, cylinder, or a sphere, rectangular coordinates can make the equation look complicated. So new coordinate systems often simplify the geometry. So the main idea behind this is simple. Choose the coordinate system that matches the symmetry of the problem. So let's start with cylindrical coordinates. So we have a point xyz in the space, and this blue plane is actually xy plane. So let's bring this up, straight up to the level z is equal to z, if it makes sense, because initially it was at level z is equal to 0, that was xy plane, and now this is at level z is equal to z at the height of this point. Now think of polar coordinates, and for this join this point to the tip of this arrow, and this is actually distance of the point from z-axis. Let it be r, and let theta be the angle between positive x-axis and the radial vector r. Draw a circle of radius r which passes through the point, and now bring everything back down to level 0 like this. So now you have this point at level 0, means coordinates of this point are x, y, 0, right? And in polar coordinates, you can write x is equal to r cosine theta, y is equal to r sine theta. Now, draw a cylinder with this circular base and height z is equal to z. Then coordinates of this point becomes, since we initially had xyz and x is equal to r cosine theta, we have already proved that, and y is equal to r sine theta. So this height is the z coordinate of this point, and that z is equal to z. This is same z as z is in rectangular coordinates. So this is the transformation equation. From cylindrical to rectangle, we have these three equations: x is equal to r cos theta, y is equal to r sine theta, z is equal to z. And from rectangular to cylindrical, we have these three equations, and this equation actually gives us r is equal to square root of x square plus y square, and theta is tangent inverse y by x, and z is equal to z in both the cases. So whenever we require to convert cylindrical to rectangle or rectangle to cylindrical, we are going to use these transformations equations. So let's move to spherical coordinates. Spherical coordinates are 3D analog of polar coordinates in plane. So let's have a point xyz again in the rectangular coordinate system in space. Let's join this point with the origin, and let this distance be rho, and draw a sphere of radius rho. Then this point lies on the sphere of radius rho. Now we have to find xyz in terms of rho and the angle between this line and z-axis, and angle between this line and x-axis. So let's try to do that. This is the trace of the sphere with xy plane. Let's draw a bigger circle which passes through the endpoints at z-axis upwards and downwards, that is north and south. And let's draw the angle. This is the angle between this radius vector and the z-axis. Now let it be phi. Phi lies between 0 and pi. So this is another coordinate, spherical coordinates. So rho, phi, and third coordinate would be theta. For this, in order to find theta, let's draw a horizontal circle which passes through the point and bring this circle to xy plane. Now we have this point, projection of this point onto xy plane is this. Now join this with origin. Then this is the angle theta, which this r makes with x-axis, and theta here lies between 0 to 2 pi. So we have rho, we have phi, which lies between 0 and pi, and we have theta, which lies between 0 and 2 pi. Now we have to write x, y, z in terms of rho, phi, and theta. So let's do that. So this is the relation between r, phi, and theta, and this is the figure which represents all of them. You can see that here r over rho. R over rho is sine phi. Similarly, this distance is z. So z over rho is cosine phi, right? And this gives us tangent phi is equal to r over z, and r is equal to rho sine phi. Similarly, z is equal to rho cosine phi. Now let's write x, y, z in terms of r theta phi. So we have x is equal to r cosine theta, y is equal to r sine theta, where r is rho sine phi. So x is equal to rho sine phi cos theta, y is equal to rho sine phi sine theta, and z is equal to rho cos phi. And this is the transformation from spherical to rectangle. Similarly, we can transform from rectangle to spherical by using these results. Rho is the radius of the circle, so rho is equal to x square plus y square plus z square square root, and this is also the distance between origin and the point. Tangent theta is y over x. So theta can be written as tangent inverse y over x, and tangent phi is r over z. R here is x square plus y square square root over z, and phi can be written as tangent inverse x square plus y square over z. So these are the transformation equations of rectangular and spherical coordinates. So this is a summary of the transformation equations. We can transform from cylindrical to rectangle, rectangular to cylindrical, spherical to cylindrical, cylindrical to spherical, and similarly spherical to rectangular, rectangular to spherical. These are the transformation equations where we need to remember that r and rho both are non-negative. Theta lies between 0 and 2 pi, we have already discussed, and phi lies between 0 and pi. And there are few surfaces which can be described in each of the coordinate system. We are already familiar with the equations of these surfaces in rectangular coordinate system, and these can be these can also be written in terms of cylindrical and spherical coordinates. So if we have equation, we already know that equation of cone is c square is equal to x square plus y square, but the upper half of the cone is z is equal to square root of x square plus y square, so it can be written as z is equal to r in cylindrical coordinates, where phi is equal to pi by 4 in spherical coordinates. Similarly, we have equation of cylinder with the circular base centered at origin and radius 1. X square plus y square is equal to 1. And this can be written in cylindrical coordinates as r is equal to 1, and in spherical coordinates rho is equal to cosecant phi. And similarly, we can transform sphere, paraboloid, hyperboloid, and several other equations in terms of rectangular, cylindrical, and spherical coordinates whenever needed, and whichever is easier to describe or easier to manipulate. So that is all for today's lecture, and that is also the end of chapter 11. So in next lecture, we'll be starting chapter 12. So till then, take care. Bye.